Okay, it's time. So, gentle reminder, quiz number 17 and 18 are due this Friday. And good thing is this, we don't have PA due this week. Great. Oh, but by the way, PA8, the next one, is now available online. So if you go to the PA, the assignment link of the course webpage, you'll see it. And the topic for today is this. First of all, we're going to introduce what's network congestion in general and talk about the cost, okay, of having congestion. It's actually not a good thing to have and probably worse than having packet losses. And then there's going to be quiz 19, and then we'll be introducing the congestion control mechanism in TCP called the AIMD. Principles of congestion control. Now the section title sounded a bit like we're going to talk about these general mechanisms to do congestion control. Well, but no, in 3.6, what we're going to talk about mainly are what's causing the congestions to occur. What is so bad about having these congestions? So hopefully from the discussion you see a little bit the nature of congestion and the design elements of doing congestion control. Congestion is this thing, having too many sources sending too much data too fast into the network. And by network here, I actually meant the core of the internet. All right. So congestion here sounds a little bit also like the problem we see in TCP, such that we need flow control. The situation there is that the TCP source sending too much data too fast into the receiver buffer. So the congestion there occurs at the receiver. And the resources that's being exhausted is the receiver's buffer space. Now when we're talking about network congestion, congestion is occurring here. Routers. And these are the machines that are in the core of the internet. And the resources that we're exhausting there when congestion occurring are these, the buffer space. So router buffer is the resource that we're trying to handle. Now when we are all sending data into the core of the internet, you see that these buffer space can quickly be exhausted. If not, hey, we will have to wait a long time, or these packets will have to wait a long time, right, until they get served. So what's bad about having congestion is this. We see packet loss when the buffer overflows, or long delays when there are lots of packet waiting there to be served. Congestion there is one of the top problems in computer networks, just like reliable data transfer, and probably a little bit more serious than reliable data transfer these days. Coming ahead is a series of these scenarios, growingly more general, and hopefully by the end of the discussion, you see congestion is something that's really bad. You could invest a lot of time, a lot of resource, but you ended up having nothing. Scenario 1 is this. Okay, you see here, we have two senders, host A and host B, two receivers. Okay, so two servers receiving requests, I suppose. So two senders, two receivers. And we do have a link in the middle. The capacity is what? R. There's a router on the link and carries infinite amount of buffer space. Cool. So what that means is that there are no packet drops, because it just takes a long time for the packet to go, but they are never dropped because we have infinite amount of buffers. Now let's assume that there's no bit error, therefore there's no need of retransmission because there's no packet drop and no bit error. Okay. Now let's use lambda here to denote the rate host A and host B are injecting data into the network. Okay, so host A and host B are actually raising the rate, okay, as time goes. Let's use lambda out to denote the amount of data that arrives at the receiver. Now, when lambda in is really low, starting from here, when we increase lambda in, the more data we send in here, the more data comes out here. Okay, so lambda out will actually increase accordingly. But this will only go up to here. When we exceed the link capacity, because there are two flows and link capacity is R, so each flow gets only half of R at best. That means lambda out here can only, at best, being R divided by 2. So even though lambda in continues to send more, but no, we hit the limit, hit the ceiling here because resource is limited right here. Okay, we don't get to push more out. So increase sending rate, receiving rate accordingly. But here, even though we're increasing the sending rate, but the receiving rate remains the same. Now, the delay is going to show this way because when lambda in continue to increase, as you reach half of R, it reaches also the link capacity, right? Because this is also half of R, this is also half of R. And so at here, it's R completely occupied. So when we approach the link capacity, the queuing delay is what? Approaching infinity. So the first bad thing you see already, long delay, when we send a lot more data and more than what the network can accommodate. And scenario 2 is actually very much like scenario 1. The only difference is this. The buffer space in the router there in the middle now has only finite amount of space. So in scenario 1, we have infinite buffer, so we don't have packet drops, right? So what's bad about that scenario is just we will have long delay. But now in scenario 2, we have finite buffer space, so potentially we could have what? Packet drops. So potentially we need to retransmit packet. And retransmission here is at the TCP layer. So if lambda in is what the application layer process is generating the data to send out to the network, that lambda in prime denote the amount of data the transport layer needs to send into the network in order to complete the job. Okay? Then we'll see lambda in prime should be greater or equal to lambda in, because it should definitely contain the amount of data we need to send out, and plus potentially retransmissions of some of these data. Right? Lambda in, lambda out, the same thing. At the application layer, lambda in is going to be very much like lambda out. How much we send out, in the end, at the end of the time, lambda out is going to come out. And that was just to describe scenario 2. Now, let's assume the sender knows perfectly well when the router buffer is available. Okay, so sender sends data out only when there's buffer available here. So no packet drop. The scenario goes like this. At the transport layer, now we keep a copy of the data just in case we need to retransmit. But the packet will arrive at the router because there's free buffer space, so it travels through the network, reaching the destination. Okay? And that goes back and we remove the copy. Right? So this is when the sender has perfect knowledge of the routers in the middle of the internet. Now in this case, there's no need of retransmission either, so lambda in prime is essentially the same as lambda in, and lambda in is essentially lambda out. So you see the same curve. We could have lambda in increasing and we get the same lambda out up to the capacity of the link. To be more realistic, let's assume sender does not know whether the buffer space in the middle here is going to be free or full. Okay. So we'll have packet loss this case, because when the packet arrives at the full buffer, it's going to be dropped. And in that case, they will have to resend the packet. So packet arriving at the transport layer, at the sender side of transport layer, we keep a copy. Now, that packet arriving at the router sees buffer full, so drop the copy, and the sender there waits for some amount of time and retransmit. And this time, it happens to be free and it passed through. Receiver there, receiving the packet, sends back acknowledgement and removing the copy of packet here. And you see, at the application layer, there's only one packet being sent. But in the transport layer, we send 2 times the same copy. So lambda in prime, the output rate at the transport layer, it's definitely going to be higher than the output rate at the application layer. Now the output rate at the application layer for TCP is going to give you the same thing at the receiver end. Therefore, you see lambda in prime versus lambda out. It's going to be lambda in prime higher than lambda out. So in the end, even though the lambda in reaches its capacity, half of R, okay, but we don't get exactly half of R out here because some of these half of R is going to be used for retransmission. So this margin here, unfortunately, is used for retransmission. So the actual amount of data coming out, less than half of R. And you see here, the bad thing, number 2, we have retransmissions when there is congestion here. To make it even more realistic, we know earlier when the buffer is full, the packet can be lost. The thing is that at the sender side, in order to detect if there's a buffer full, if there's a packet loss, we set up timer as well. Okay, so these timer can go out prematurely and therefore sending copies while we don't really need it. So it's illustrated by the animation here. Data coming from the application layer process, we keep a copy at the transport layer sender just in case we need to retransmit. Now let's assume that the buffer is free, but in case the timer is too short, we time out prematurely. We ended up sending 2 copies of data here, okay, while only one copy of it will be arriving at the application layer. So lambda out remained the same as lambda in, but we see here, the lambda in prime, this is going to be higher than the lambda in prime in the previous assumption, where we do not assume the timer can go out prematurely. So the performance of lambda out here as lambda in prime increases is going to go slightly worse. The margin here is going to be bigger because what? Lambda in prime here, we need to take into account the retransmissions. Now we also need to take into account the duplicates that are not really necessary. So we see delay being bad, retransmission being bad, and what's even worse is that we could have unnecessary retransmission. Now if you think about it, congestion, we see that having packet loss, having delay, not good. But to address packet delay issue, to address packet loss issue, we need a retransmission mechanism, the RDTs. As a result, what? We are actually generating more traffic into a already congested network. So the cost, okay, of congestion is actually not that trivial. Okay? It's not just that the delay rises, it's not just the loss increases, but also the traffic being dumped, injected into the internet also increases. So in the end, the internet is doing even more work, while the throughput is not getting better and sometimes even worse. As you see, the margin here is bigger than the previous case. If you think scenario 2 is bad already, where we do more work, right? Lambda in prime increasing, but lambda out increases at the beginning but saturates toward the end, okay? So beyond certain point, the more work you do, you don't get more results. Okay? But here, I'm going to show you an example. Yeah, at the beginning, the more work you do, the more results we get. But in this scenario, the more work you do, you might end up having less results. And the even more work you do, the even less results. And here's the scenario. We do have 4 senders now, or 4 hosts, A, B, C, D. Okay. And each of them is generating a flow traveling multiple hops. So this is one hop. This is the second hop for the red flow. multiple hops. And yeah, we might run into buffer full situation, therefore we could have packet drops, and therefore we do need a transport layer mechanism to try to do retransmission. So similarly, we have the lambda in, which is the input rate from the application layer, and lambda in prime being the input rate of traffic into the network from the transport layer. Okay. Now let's focus on the red flow coming from host A and the blue flow coming from host D. Okay. And these flows will increase the sending rate lambda in. And therefore, lambda in prime will also be increasing, and sometimes increasing faster than lambda in. Now what's going to happen when lambda in and lambda in prime increases? Now, at the beginning, you see the red flow, the red packets coming into this router here. Okay. And as the rate increases, the buffer space here is going to be occupied by the red packet, just like the blue packet in the meantime, coming into the first hop router and occupying the front sections of the buffer space in the router there. Now, after a while, the red packet is going to come out and enter the second hop. Just like that, blue packet is going to come out and enter this router here at the top. And the blue packet will be coming in to compete with the red packet that is already occupying most of the buffer space. Okay, so this is already pretty full when the blue packet just arrived. Okay. And as the lambda in increases as well, as they both approach a half of R, you see this. The buffer space is going to be very full, and quickly, red packet will be dropped, but blue packet will be dropped even more, because very few of these blue packets get into the queue and have a chance to go out, finally reaching B. So as lambda in prime increases, the arriving blue packets at the upper queue here, most of them get dropped, and therefore the throughput very small. So you see right there in scenario 3, the blue flow, right, when lambda in or lambda in prime is small, right, when the network is not saturated, when the buffer does not overflow, then the more work we do, the more output we get. But as it approaches half of R, we see blue flows, blue packets gets dropped a lot. So originally not so bad, but in the end, when buffer flow could occur here, blue packet gets very little chance of coming through, and the throughput is going to be even lower, okay, than when the lambda in here is small. Okay? Really bad. So that is another cause of the congestion. Because what? The bandwidth that is transmitting these packets when they're traveling upstream, okay, it's all wasted. The amount of waste is actually not quite comparable to retransmission or unnecessary retransmission. Those are probably very small. Therefore, in the lambda in and lambda out plot we saw earlier, the margin is very small. But here, the upstream bandwidth, those are all wasted. Okay, so the amount of resources we are wasting here could be very high. Okay, so the hidden cost here, waste of all these upstream bandwidth resource, and this is a big cost. So message here, congestion, really bad. But what can we do about it? All right, so that was how bad congestion can be, and the cost of having congestions. The reason that Polly asked you guys how you guys are doing the semester is actually related. The number of courses or number of credits you can take is also, okay, like the data you want to inject into the network. Okay? And your brain capacity or your time, okay, you have is like the buffer space. Okay? When the data, when the amount of work you need to accommodate exceeds the brain capacity, exceeds the time capacity, then you run into congestion here. So after midterm or right at midterm, you're probably seeing a peak of the load there. Okay, therefore you're feeling that there's some sort of congestion happening. Just be careful though in the second half of the semester. Okay? You want to pace yourself, okay, and use your time well or use your brain capacity well so that you can accommodate the workload that's coming ahead before the final. Okay, so that's just so that I bring an analogy to you. There's another analogy I would like to bring to you is this. So quiz number 19 is also a bit open. Okay. The way of thinking of addressing a problem is often this. I will actually take myself away from the context and then seek a system that actually is similar, okay, and try to address the system that's existing that I'm experienced with and for a solution. Therefore, I can borrow the solution from this system that I see I've experienced to a new system that I'm designing. So let's suppose that the internet congestion is happening and we want to be able to handle the congestion. How do we do that? Now let's seek a solution in the highway system, okay, the traffic system. And quiz 19 here is asking you to pretend that you're an Uber driver. And what you do is to drive a lot between the city center to the airport. Okay, so this is the main line you're serving. And you do have a situation here. You're currently on the highway number 1 and driving from the city center to the airport, and you see it's highly congested. Q1 is asking you this. Can you name a couple reasons that's causing the congestion? So just name a couple that are likely the reasons behind the congestion. Sometimes you don't really see the congestion point, right? So you're probably way behind and get stuck there on the freeway. So yeah, what might be the reason? Q2 is asking, now you're stuck on the traffic, in the traffic. Can you inform your other fellow Uber drivers so that they do not get onto the freeway and add to the congestion? Okay, so maybe they can also just take a different route to avoid the congestion that's happening here. So Q1, reasons for the congestion. Q2, how are you going to inform, okay, all these other Uber drivers? Yeah, so let's allocate some 5 minutes for the problem so that you can brainstorm a bit more. Okay. Ways to inform the other Uber drivers. Oh, wow, David, really fast. Team 2 here. All right, Q1. We're driving at rush hour time. Yeah, that's one very likely reason, because there are just a lot of cars on the freeway. Or peak hours, yes. Or maybe there's an accident, yes. That's also the common cause of a congestion. Q2, report to the office. Okay, so you actually tell the Uber main office and let the Uber main office send a notification to the other drivers. Very good. No problem. Oh wow, suddenly, very good. C196A that we can know the condition of high. Oh, okay. Interesting. So is 196A a certain website? How you? Can you tell me, yeah, what's 196A? I actually don't know about it. Interesting. And Rocket is saying a lot of demand, yes. There is a loss of bandwidth issue, car crash, perfect. A tree falling onto the legs, sure. Bridge collapsing, yeah, I hope not, but yes, that's one possible reason. Q2, using an alternative medium such as the cellular network. Okay, yeah, so yeah, make a call. Or post information, yeah. So ask your customer, right, to type up something from your phone and to the Uber system. Yes, definitely. Okay, social media, navigation software. Oh, wow, Waze. Okay, cool. I also have Waze downloaded on my phone. Okay, that's a very, very cool system. Yeah, I think Waze was one of the first, isn't it? And Kevin, that's team 4. Too many cars on the highway, too fast, definitely. Just like, how internet gets congested. Some part of the highway under construction. That's, yeah, perfect. That's, yeah, one of the very common cause of having congestion. And, okay, yeah, how you telling me now? Yes, there's 高速公路 1960A. I see. It's an app. Okay, perfect. And RNG Silvercraft. I think you're Yizhou, right? Congestion might happen due to rush hour, definitely. Car crash that blocked the traffic. Perfect. Okay. Yeah, I'm just going to come back and complete the quiz 19 complete list a bit later. So essentially, yeah, lots of different causes. Rush hour, too many cars onto the highway too fast. Accident, construction, other obstacles blocking the way, or some of the bridges on the highway collapsed. And the potential fixes is just, to typing on the app, okay? Or use social media to inform the friends who are probably also Uber drivers. Great. So you see that. Chance is actually high that TCP, handling congestion control, is taking a similar way, right? First, by observing a congestion, and second, informing those who are regenerating more traffic onto the highway to try to do something, maybe slow down or take a different route. And that takes us to the second part of the lecture. Scenarios elaborated. You see, particularly in scenario 3, the only solution or the only effective solution to a congestion is to what? Just slow down. And therefore, the 2 key design elements in a congestion control mechanisms are these. First, detecting when a congestion is occurring. Second, notifying the traffic sources that's causing the congestion to slow down. And there are two major approaches allowing us to achieve those. First is called the end-to-end based approach. The other, the network-assisted approach. Now, from the name of it, you probably guessed. Yeah, end-to-end meant the end systems are doing much of the work, detecting congestion, informing the traffic source to slow down. Network-assisted, on the other hand, is asking the routers to do all these work instead. Let's first focus on the end-to-end approach. So in this approach, the end systems will need to infer if there is a congestion occurring inside the network. If you recall back in TCP, okay, what we're doing is sending multiple packets in one flight to the receiver. Receiver sending ACK back. And all these packets and ACKs carry the sequence numbers. So receiver can actually detect a gap, okay, in the packets being received, and therefore sends duplicate ACKs instead of new ACKs. So receiving duplicate ACKs is a way of detecting if there's a loss, or the sender side can simply time out and then retransmit. That's also a signal of detecting there's potentially congestion inside the network. So that is, observing from the loss occurring, inferring there's a congestion. One can also observe if there's delay changes. Okay, so for example, when we send packet out, let's track the sending time. Okay, let's track also the time when the ACK for that packet comes back. Calculate the difference, you get the round trip time. And if you observe for a long enough time, you might see, oh, the round trip time is increasing. When it goes beyond a certain threshold, then you could say that also, network is running into a slight congestion there. Okay, so overall, general mechanisms, observe packet losses. If there is an increasing trend, observe the delay. If there is an increasing trend, then you're going into this hotter zone where congestion is likely occurring. Now, taking this approach, we do not get explicit feedback from the internet, from the routers inside the internet. And taking the end-to-end approach, we'll have to also guess or infer the right sending rate. Okay, so this is for the source to know exactly what is the right rate to send the data so that we do not overwhelm the network, in the meantime not being too conservative, too slow sending the data out. And this is actually rather hard to do for the end systems. After all, they are actually at the very edge of the network. The congestion could be happening anywhere inside the network along the path. So what the end-to-end approach is doing is this, okay, guessing. By trying a certain rate and observe if there's a loss, okay, if there's a growing delay. If not, then cool. This is actually within the available bandwidth. So maybe let's raise the rate a little bit and see, right, if there's a loss now, if the delay increases now. If not, then hey, we're still safe. Let's, increase it so that we're not too conservative, too slow sending the data out. Now, but if we exceed a certain point, and as a result, we begin to see loss, and we begin to see the delay increasing drastically. Yeah. That is actually not good. That indicates that we are probably exceeding the available bandwidth threshold, and therefore we are sending data too much, too fast into the network. So if we are failing, if we are detecting the signals of congestions, then that's slowed down. Okay, so end system here to infer, to find out what is the right sending rate is by trying. Okay, pushing. If we over push it, let's come down again and then try to push it again. Well, if not good enough, slow down again. All right? So this is in fact the approach also taken by TCP. This is actually very natural because TCP being a transport layer protocol, it's actually implemented receiving side, sending side both at the end systems. Therefore, it implements an end-to-end based congestion control mechanism. The network-assisted approach. Okay, so in this approach, routers will be doing the congestion detection. But how? Well, we also need to observe something, but this time we could actually observe something that's very directly related to congestion. This. the queue size. Okay, so this is the queue of these packets gathering at the entry point of a router. Okay, so congestion is this: sources of the traffic sending data too much, too fast into the network. Inside the network, we have these routers, right, handling packet forwarding. If the outgoing rate is slow and incoming rate is high, then these packets will need to what? Be buffered temporarily, okay, at the entry point of these routers. And therefore, they get a chance to wait for their turn to go out on the outgoing link. If the outgoing rate is slow, incoming rate is high, queue gets long, and free buffer space gets small, right? So queue size or free buffer space, okay, changes of these, okay, are good indications of a congestion occurring. Now, routers, however, are the devices in the middle, okay? How do the routers inform the sources so that the sources know that they need to serve them? Yeah, this is the way it's done, okay? So there are these bits, special bits, okay, inside the packets. So when these packets travel through a router, and the router is so busy, queue size is so big, or free buffer space is so small, these bits get turned on. Okay? And when the packets arriving at the receiver, receivers can check these flags or check these bits and then inform the source of the data, the sources of the packets. Okay. Now, in Internet, okay, the TCP/IP protocol suite, okay, yeah, let me explain. TCP is actually a transport layer service, okay? But sometimes we also call the transport layer the TCP layer. IP is actually a network layer protocol, and therefore sometimes we actually refer to the network layer as the IP layer. So TCP/IP here is actually referring to the Internet protocol stack because the transport layer is running TCP. The network layer is running IP. So these two are the very typical classical protocols that are running, okay, supporting the operation of the Internet. So in TCP/IP or in Internet, we have these special bits, and we call them the explicit congestion notification bits. So when the router inside the Internet, the queue size gets large enough or the free buffer space gets small enough, we set the ECN bits on. And therefore, the receiving end, the TCP receiver there, seeing the ECN bits on can inform the source to serve them. Now, that is how the routers in network-assisted approach detect congestion and notifying the source of the congestion. What's nice about this approach is this: the routers there observe exactly how much free space there is, okay? And dividing by the number of flows that's going through, number of connections that's going through. Hey, routers can also be more explicit, telling the receiver to inform the source. Now, set the sending rate to this size. Set your sending window size to a particular size, such that we will not be overwhelming the router buffer space. Just like the flow control mechanism, right? Receiver there observing the receiving buffer, depending on how much is free, set the sending window size accordingly, and voila, problem solved. Receiving buffer will never be overwhelmed. Similarly, the router's receiving buffer here will never be overwhelmed. And we'll take a look at an example of an end-to-end based approach, TCP's congestion control mechanism. And TCP does it this way. The sender will increase the sending rate gradually if there are no packet losses detected. But as soon as there's a packet loss, we drop the sending rate drastically. So point number one here. Packet loss is used as an indication of network congestion in TCP. Point number two. TCP is actually implementing a trying, failing process to discover what is the proper sending rate. Now, by sending rate here, I'm adjusting. In TCP, it's implemented this way by changing the sending window size. You see that the sending window size is a limiting number of bytes we can send out within one round trip time. Therefore, increasing the sending window size is increasing descending rate. Okay. All right, the exact process of doing the trying and failing is called the additive increase, multiplicative decrease, or AIMD to be short. So AI describes the increasing process of the ascending rate. So this is done by setting the window size and such that it increase one packet per round trip time. And the decreasing part is this cutting the window size to half of it, okay, after detecting a packet loss. So you see the increasing part is slow and linear. The decreasing part is drastic, multiplicative. So additive increase, multiplicative decrease. Okay. Linear increase, multiplicative decrease. So if I show descending window here over time, we'll see when there are no losses, the window size is going to grow linearly. As soon as we hit the loss, we drop the window size drastically to half of it. So additive increase, multiplicative decrease. So each of these AIMD episode looks like a sawtooth. And that is why people often say TCP's window size change over time shows a sawtooth behavior. One thing I want to add is this. We say we increase the window size by one packet per round trip time, but TCP sequence size is counting data by bytes. Window size is therefore also counting the maximum amount of data we could send out by bytes. So what do we mean by increasing the window size by one packet? That doesn't make sense. How do we implement that? Yeah, so the fact in the implementation, what's being done is to increase the window size by one maximum segment size. Okay, so MSS here, if it's configured to be 1460 bytes, then the window size is incremented by 1460 if there's no loss detected within a round. And this is actually related to the second point I want to stress. Yeah, you see here, the full name of the sending window is no longer WND. Right? It's actually called the congestion window size, CWND. Because the sending window size is dynamic in TCP, and it's actually controlled by the congestion control mechanism. That's why the window is now referred to as the congestion window. And this is TCP's process of trying to probe and discover the available bandwidth. Now let's bring up the diagram we used to explain TCP. Now it's counting bytes. Now each of these is what? A byte. If we'll be generating a new packet, then we'll be using the byte stream number here as the sequence number of the new packet. Right? So what you're seeing here is I'm updating the diagram such that this term here is no longer WND, the sending window size. We are now calling it the congestion window size, okay, because this here, okay, CWND is dynamic. It can be large or small. It's no longer a fixed size. And how large it is depends on how the network is smooth. How small it is depends on how bad the network is congested. And the quantity CWND here limits the number of bytes there can be between the last byte sent to the last byte act. Last byte act. So green here are counting the bytes that have been sent and have been act. So the last byte act is the last screen. Yellow here are the packets sent or the bytes sent but not yet act. So last byte sent is here, the last yellow. Okay. So last yellow, okay, subtracting the number of the last screen. That means the number of yellows. Okay. So CWND here limits the number of yellow bytes there can be at best. Last. So we say TCP's congestion control is done by controlling the sending rate or changing the sending rate to discover what is the right one. We already mentioned earlier that is actually implemented by changing the window size, changing the congestion window size, because the sending rate is essentially the congestion window size divided by RTT, because within a round trip time we can only send these many bytes. Something that's a little bit unusual in TCP's process of discovering the proper sending rate is this. There's an initialization phase, and the mechanism is called the slow start. Okay. What it does there is, when TCP is just starting, a connection is just starting, the initial window size is set to 1 MSS. And the increasing pace is no longer AIMD, it's actually what? Doubling the window size per round trip time. AIMD is what? Increasing the window size by 1 MSS per round trip time. Wow, so that's actually quite aggressive, isn't it? You are correct, because the window size in slow start, in the initialization phase, is going to increase exponentially. Because every round trip time, you double the size. Every round trip time, you double the size. As opposed to in AIMD, every round trip time, you increase by 1 segment size. Every round trip time, you increase 1 segment size. Right, so yeah, the initial rate, very, very small, 1. So a slow start is actually referring to, yeah, the initial window size being, yeah, the lowest possible. But the increasing rate is actually exponentially fast, okay? So this is actually the part of design in TCP's congestion control that can confuse you a little bit. It's slow start, but it's actually increasing really, really fast, right? So the intuition says this is fast start, in fact. Okay. Yes, you are correct, but the slow here actually meant the window size, the initial value, is a very low value. Okay. The last point I want to make is this. Okay. Doubling window size per round trip time in the implementation is actually done this way. Okay. Window size is incremented by 1 after receiving an ACK. Okay, so look at the illustration I have on the right. A is the sender, B is the receiver. A originally in slow start having a cwnd of 1 MSS. That data packet will go, receiver here will send an ACK back. Host A here being the sender, receiving an ACK will do what? cwnd plus plus, and the increment is 1 MSS. As a result, it was originally 1, now 2. Therefore, sender here can send 2 segments in MSS. So these will go and generate 2x coming back. Sender here receiving 2x will be calling this line twice, therefore 2 will become 4. Similarly, 4x comes back here, and this will be called 4 times, therefore the window size becomes 8. And the next round, 16. You see an exponential increase here, right? By a factor of 2, isn't it? So overall, TCP's process of discovering the proper sending rate is more like this. This is a TCP connection. And this is the beginning of it, and this is the end of it. So there's this initialization phase where we run the slow start mechanism. Okay, and the behavior of the window size is AIMD. And then in the steady phase, we run this congestion avoidance mechanism. The behavior of the window size is AIMD. And perfect timing there. So that concludes today, and we don't have further questions, so that's all for today. Come back again tomorrow, and that's all. I'm gonna leave the session running for just a few more minutes in case you have anything to ask. Otherwise, I see you tomorrow. Ciao. Alright, so that's all. I'll end the stream now. Okay. Bye guys.